In today's lecture, we start to learn the last section of this chapter, section 2.5, coverage modifications. This is the most important section of this chapter and will be one of the most important topics of the entire course. So this section is very, very important. In this short video, we will start with the deductible, and we will use maybe 2 or 3 small videos to finish all the modifications. I'm sure the idea of modification is nothing new to all of you. We all have seen the concepts before somewhere in our daily life, because all the important modifications we study here are used in everyday insurance products. That's why, when we see deductible, policy limits, co-insurance, they are not exactly new to us. They are not new to pretty much everyone. As long as you have a car, you will need to buy auto insurance, and it's very likely that there is a deductible of your auto insurance. For your healthcare, it's very likely that you have a co-pay or co-insurance, etc. So those are the concepts we will be studying in the next few videos. So let's begin with the basic introduction of notations. We have already used X to denote the claim size. So that will be the amount paid in a loss event. So basically, you can think this as the claim size. So sometimes I may use the word ground up loss or original loss. Okay, X, you can think it as the starting point of all the analysis here. And then we have XL. XL is the amount paid in a loss event when there is a coverage modification, and we will start with deductible. Okay, XP will be the amount paid. So let me use a simple example to help you understand the difference between this. So let's say I have a auto insurance, okay, and unfortunately I bump into an accident. It costs say $2,000 to fix my car. So let's say I hit the animal, okay, so I hit a deer, and it costs $2,000 to repair all the bumpers, all the lights. So that's the original loss, the starting point of the analysis, right? For an insurance company, the analysis begins, or the claim analysis begins when something happens, right? In my example, I hit a deer. So that's the starting point of all the story. Okay, so let's say for my insurance, I have a deductible of $500, which is rather normal in many policies. That means for my particular policy, any loss less than $500, I will need to pay all of them. The insurance company does not cover for small amount claims less than 500. But here, luckily or unluckily, the size of my claim is more than 500. So this amount will be break into my portion I pay, because there is a deductible, right? So I will need to cover all the losses up to deductible. So in this case, the entire deductible will be used because the amount of loss is bigger than the deductible. So I pay the entire deductible. The extra, which is 1,500, which equals X minus D. Okay, I put plus. Plus means the positive part. If X is smaller than D, then it's 0. If X is bigger than, so the meaning of this is this will be 0 if X is less than or equal to 0. This will be X if X is bigger than 0. So this is what we call the positive part, right? So if you have a negative number, the positive part is obviously 0. If you have a positive number, the positive part is obviously itself. So in this case, this will be my insurance company. So in this particular claim, the entire amount is 2,000, which will be divided into two parts. The first part, 500, I will need to pay. The next part, $1,500, the insurance company needs to pay. So that's how we do the analysis. In this particular case, this will be XL. Okay, it's the amount paid in a loss, in a loss event. Okay, the key thing here is what is a loss event? What is a payment event? So a loss event is when a loss happens. So basically when an accident happens, okay, or a significant event happens as defined by the contract. So this is pretty much, you can think something happens. Okay, what is a payment event? Let me get a different color because they are totally different. Okay, a payment event is when the insurance company needs to pay. So here XP is the payment, is the amount in a payment event. A payment event is an event when the insurance company needs to kick in to settle the claim. Okay, so in this case, so let's call this example 1. In the first example, the loss amount, the total loss amount is 2,000. Okay, and the amount paid in a loss event here in this particular case with the deductible XL is 1,500, and it is also the amount paid by the insurance company. So in this particular case, XL equals XP. Okay, but of course this is not always the case. Let's say if you let me use the same example, example 2. So still the same accident. The cost is $2,000. Okay, but now the it's not deductible. So let's say I have a co-insurance. Let's use C, 20%. So that means as long as something happens, I cover 20%. My insurance company covers the remaining 80%. So I'm going to separate this into 400, 1,600. Okay. So in this case, we have something slightly different because we both, this is my portion, this is insurance company portion. Okay, so in this modification, what I have is a co-insurance. So how I calculate this number is, this is the entire amount times the co-insurance portion. This will be the entire amount times 1 minus it. Okay. But sometimes the payment event. Let's get another example. Example 1.1 or example 1 prime. Okay. So in this case, I still have the deductible 500. I still have an accident, but this time I'm lucky enough. This is a small scratch. I only need to pay $200 to fix my car. Okay. In this case, XL is 0. Okay, because the insurance company doesn't need to pay. Right. I paid the full $200. So this is a loss event because something already happened, right? That's why I had to pay $200 to get my car back to its original shape. But this is not a payment event because I pay the entire $200. The insurance company doesn't need to be involved, right? I will not call my insurance company because I already know the amount is $200 and I have 500 deductible, right? Even I call them, they will simply ignore me, right? So from this example, we see there's a difference between loss event and payment event. We will get to the technical side of the difference. Here, I only introduce 2 or 3 examples to give you a quick idea of the the modifications and how they can be applied in real life situation. Now let's do the first one, deductible. Deductible is very common in auto insurance, right? This cost is for short term. Auto insurance is one of the most important policies for short term policies. Okay, I already used the car insurance example, so you should already know the meaning of D. Right? D stands for deductible. It is the first letter of deductible, and deductible is obviously a positive number. Of course, if you really want, you can put 0 as one of the possibilities. Right? If D is 0, means there is no deductible. Okay. By definition, the amount paid in a loss event is given by, I prefer this because this is the uniform notation. Right? Otherwise, you need to write into this piecewise form in 2.69. This is the positive part, which I already introduced. So it's very easy to see they are equivalent between those two expressions. So it depends on your preference, which one you prefer. You can either write it in piecewise here, or you can write it in one expression as using the positive function. The idea of deductible is too easy. I mean, I don't need too many words to describe what it means. Next, there's a graph, but I think I will use the next slide to give you more ideas of the meaning. So we already know the definition of XL. XL is X minus D, take the positive part. So we want to know the PDF of this new random variable. By the way, this is a new random variable. If you look at the definition, you start with X. X is given. What you apply is this functional form, right? So first of all, you subtract by D and then take the positive part. Mathematically, I can say I apply a special function on X in order to get XL. So this is a slightly special transformation to get new random variables. Okay, how do I derive this? Okay, I will get to this in a moment, but let me introduce another concept, which is XP. XP is the amount paid in a payment event. So this is really important and likely the confusing part to some of you. So remember, in this small subsection, we study deductible, okay? And because of the deductible, it's possible that something happens and the insurance company doesn't need to pay, such as the example I just gave. The X equals 200 and deductible is 500. All right, so something happened. However, the insurance company doesn't need to pay. In that case, X is less than D, right? So in order for the insurance company to get in to make a payment, the size of the claim must be strictly greater than D. So this is the condition for payment. So as long as the size of the loss is bigger than the deductible, the insurance company will need to pay the difference between the loss and the deductible, that is X minus D. So that's why when we define the payment Okay, the amount paid in a payment event, we need to add this condition. And since we add this condition, there's no need to put the positive part anymore, right? Given this condition, given x bigger than d, obviously the positive part I can remove because I already know it is positive. It is strictly positive. It will be equal to x minus d. So that's why here in the definition of xp, I don't need to add the positive function. It will be positive, conditioning on x bigger than d. Okay. So now let me do the analysis. Okay. So this analysis is going to be very, very important. So first, let's fix x, which is the original loss or the ground up loss. So which models the claim severity. You may want to apply one of the distributions we already introduced to model X, such as exponential, such as Pareto, such as Weibull, such as gamma, or any continuous random variables or continuous distributions you want to apply. Let's put the PDF is small f, put a lower subscript, and CDF use capital F. Okay, so that's the given condition. Now we study the first one, which is the amount in loss event. So this is amount in a loss event. Okay, by definition, we know, let me put in a box. XL equals X minus D, take the positive part, okay? So obviously there is something strange for this one. We often apply continuous distributions to model the claim severity X, but even we apply a continuous distribution, XL is not continuous. It has a singular point. It may be 0, right? So what is the probability for this part? So let's first analyze the probability at 0. So by definition, this is greater than or equal to 0, right? So what is the probability that XL equals 0? I always do definition. So that means X minus D positive equals 0. That means my X should be less than or equal to D, right? So this is the CDF of X at D. Since our D is often strictly positive, so this is likely non-zero. So it's often that you have a singular point, or sometimes we call it probability mass. At 0 point, okay? So let's say you have 10% probability at 0. When you draw the CDF, there will be a jump. So let me use a tiny graph to demonstrate. So, okay, obviously it will be 0 from the negative side. At 0, I will jump, okay? From there, I may be, some kind of increasing function. The graph is not nice because it's not fully increasing. So let me get the pen. So let's say I have this eventually converge to 1. Okay, see that this is not a continuous, this is not a discrete, this is a mixed distribution, right? For most part, it is continuous, such as the strictly positive part, it is continuous, but I do have a point here that the CDF jumps. So at this point, the CDF jumps by this amount, okay? So this is a mixed distribution. Next, let's study the continuous part. So in the continuous part, let's consider a strictly positive number, okay? We want to know the CDF. Again, this is the definition of CDF. Now I put back the definition of XL. Okay, since I want it to be less than a positive number, I'm going to take this out. This is capitalized. So my big X, the random variable, will be less than or equal to X plus D. So if I write it in integral form, I start with 0 because here X is the loss. Loss will be non-negative. Here's a typo. It should end at X plus D. Right? Again, this is the definition, right? This is how I define PDF, how I define probability density function. So from this moment, I differentiate on both sides. So I get the PDF of XL. So the only part on the right-hand side you have X is on the up point. So you differentiate the upper point and plug it in for the argument, which is S here. If your X is also in the lower point, you're going to do minus the derivative of the lower point and plug in the lower point. Right here, everything's 0, so I can simply cross it out because it's 0. Okay. So what would be the result? This differentiator is obviously 1. So I have this nice result. So in summary, if I want to write it, let's use small f to denote the joint. Well, sometimes we call this PF PDF because part of it is probability function. Part of it is probability density function. Okay, here is X equals 0. We already know this is Fx D. Okay, and here is Fx small x plus D. This x should be greater than 0. Okay, if you want, you can easily check. This is indeed a mixed PF PDF, right? Because it is greater than 0, and the summation plus the integral, it is indeed 1. Okay, so that is the analysis for the first one. Now let's do the second. Let me get one more page. The second random variable I want to analyze is XP, which is the amount paid in a payment event. Okay, since I want a payment event, I will have to condition X minus D condition on X bigger than D. That is the case when I need to pay, or when the insurance company needs to pay. So our first job is to notice that, let's go to blue color, XP is always bigger than 0. But XL can be 0. We already analyzed in the previous page. So now our question is, what would be the probability function of my XP? Okay, so now let's study. So I want to know the say CDF of XP. So first, by definition, this is the probability that XP is less than or equal to small x. Of course, here my small x is positive. I don't need to study 0. It will not be 0. Okay. So by definition, this will be X minus D less than X, but I do have a condition. So that's the part which distinguishes this XP from the previous XL. So I can do one more step, X plus D given X greater than D. Okay, now is my time to apply the definition of conditional probability. So this on top, the numerator will be the intersection of both the probability part and the condition part. So if we do the intersection, it will be x greater than d less than small x plus d, or put equal if you want. Okay, so what's the top? It will be the integral from d to x plus d fx, which is the PDF of x. Yes. So this is nothing but the definition. Okay, and I have the bottom part, which is the survival function. Let's write it in survival, right? Greater than is the survival. Okay, I can stop at this part. Now I want to know the PDF of XP. So obviously I differentiate the right-hand side. If you take a look, the upper point is the only place where I have X. So by the fundamental theory of calculus, we differentiated and substituted in for the argument, which is S. The bottom part obviously stays. Okay, the derivative obviously is 1. So let me write down in a nice box to summarize. So fx x plus d divided by sx d. So keep in mind here x is greater than 0. In the previous case of XL, x may be 0, may take 0, and it's very likely that the probability of 0 is strictly positive as long as this d is meaningful. Okay. So you can see how I derive this with everything I have. I can easily go to the theory which I want. That is the expected value. Okay, I can continue down here. What is the expected value of my loss, the amount in a loss event? By the way, this L stands for loss event, and in the next one, P stands for the payment event, obviously. So in order to calculate the probability, we apply the formula 0 times the probability at 0. So if you want, you can cross it out. 0 times anything 0. So the discrete part does not contribute to the expectation, only the continuous part. So times its density. So I directly plug in the better result. Okay. So from there, I can take change of variable. So let's use u to denote x plus d. So x goes from 0 to infinity. Then my u goes from d to infinity. X is u minus d fx. Here I switch to u. Du and dx are the same, right? Okay. So from there, what we can do is to write this in the. I think we already did this somehow before. By the way, you may keep this if you want. Okay, it's the same. So we introduce double integral. Let me use y because the part inside the bracket is nothing but u minus d. Right, and then I need to switch the order between those two double integrals. Originally, I have u bigger than d less than infinity, and I have my y bigger than 0 less than u minus d. This is the original one, and now I want my y to put outside greater than 0. Since u can go to infinity, infinity minus a number is infinity. Okay, my u is here. So I have d and the d plus, from here is u greater than d. From here is u greater than y plus d. So I take the bigger one, y plus d less than infinity. So, okay, so from 0 to infinity, now I have y plus d to infinity for fx u du. I have dy from 0 to infinity. So the inside part, will be sx y plus d dy, right? So let me change back to the pink color. So I can do dy or dx. So I can do one more change of variable to replace y plus d. So finally, it will be d plus d to positive infinity as x dx. So basically, I use x to replace y plus d. So that is the formula you will need very, very often. I just derived the formula for 2.76. You really need this formula often. A special case, let's take d to be 0. In this case, xl equals x minus d, take positive, is always x minus d. Since d is 0, is x, right? So we recover the formula we know before, right? We have already used this formula a few times. Remember, what is the condition? X is non-negative, okay? Next, we study the expected value of XP, which is the amount paid in a payment event. So from here, we know why this is correct, right? I just derived the PDF of XP. So we copy it by, well, this is the first identity is the definition of expectation. And then we plug in the PDF of XP from what I just proved, okay? And then what I do is I can take the constant out. This part is a constant, okay, as long as d is fixed, right? And on top, we can do one change of variable. I use u to replace x plus d. Of course, the textbook still use the same argument or the same variable x. So keep in mind, that's a change of variable. From there, we already know the meaning of the numerator, right? So you should know on top, this is exactly the definition of the expected value of xl. For xl, we already know for x greater than 0, less than d, xl is 0, right? Because the value is 0 does not contribute to the expectation. That is why you only need to analyze x greater than d. Okay, so we only need to know the integral part, not the summation part. This part is 0 anyway. Okay, so let me summarize this very, very important result. So you will need this result very often, not only for this course, but also for the SOA STEM exam. This is a nice result. In fact, the textbook actually offers a different idea to prove this result. That is by utilizing the Tower rule. We know for any expected value, we can write it in double expectation, but given some condition, right? So in this case, the condition is on the value of XL. You discuss XL can be either strictly positive or 0, right? XL can be only one of those two cases, which we already studied from this page, right? It can be either 0 or greater than 0. So when you discuss on these two conditions, you can write it down, right? So basically here, the condition is about the value of XL, and it takes two possibilities, either strictly positive or 0. Of course, when you condition on 0, this is 0. So that's why the second term will disappear on the next line. So you only have that. And from there, you can get an easier proof for the same result, right? So this is the result for the expectation of XP. All of you should know how to calculate those two. Since there is a connection, sometimes, let's say I want you to compute the expectation of XP. It may be easier to do XL first and calculate the condition for payment, which is just the survival function of X at D, okay? Because XL bigger than 0 is the same as X bigger than D, okay? So the final result regarding the CTE is not something that important, so I will skip that part, but it's very straightforward. I think it's good for me to end this video, and in the next one, I will do the example.